Okay, Organic Chemistry 2330. We're going to continue with chapter 14, carboxylic acid derivatives. We're going to talk a little bit more about the interconversion between the different functional groups. Okay, so like I said before, we can convert acid chlorides are the most reactive, and they can convert to the most functional things. And then as we go down in reactivity, we have fewer and fewer reactions they can do. So let's talk about the different functional groups and how they react with alcohols, okay? So if we look at acid halides being the most reactive, they react with alcohols to generate HCl plus an ester, okay? So it's a nice little substitution reaction where we have the lone pair on the alcohol coming in to attack the carbonyl and displace the chloride ion, which is then protonated by the alcohol hydrogen to give us our final product of HCl plus our ester, okay? So if we do that same thing and react an alcohol with the next most reactive species, which is the anhydride, what we're gonna get is we're still gonna get an ester because that alcohol is going to create that ester with the carboxylic acid. However, we also generate one equivalent of the carboxylic acid because one of those carboxylic acids was a leaving group, the other was the one we did the addition to. And then when we deprotonated the alcohol, it transferred to the carboxylic acid. So when we do these reactions, if we look at this lower one here, when I describe these benzoic acid derivatives, this is one of the ones we use, which was salicylic acid here. It's naturally occurring in willow bark, but it's also used when we react that alcohol portion with this anhydride, we create the ester functionality of it right here. So this becomes acetylsalicylic acid, which is the active ingredient in aspirin. Notice we generate the ester plus one equivalent of that carboxylic acid. So half of it's used to make the ester, half of it goes away as the carboxylic acid. All right, so now we can also react alcohols with esters. So we've done carboxylic acids and anhydrides, and now we're going to react with esters. When we react this with esters, we actually have to catalyze this with acid. And because we're replacing one alcohol of the ester with another alcohol, we call this transesterification. So we're transferring one alcohol with another, therefore we get transesterification. Now we typically have to have a reason to do this. So in the case of this reaction here, we have a methyl ester of this benzoic acid here, and we're reacting it with an alcohol which a much higher boiling point, okay? So the idea here is by adding a catalyst and then our acid here, we can convert this methyl ester into this glycol ester, and we'll liberate methanol. Methanol has a very low boiling point, and we typically boil that out of the reaction to drive the reaction to completion, okay? In this case, we have two alcohols on our material, therefore we're making a diester of our system, and so we call this ethylene glycol dibenzoate because we've created two esters on this ethylene glycol functionality. But again, the driving force is the fact that we have a lower boiling alcohol being boiled out of the solution. If we put in a whole bunch of methanol and add more acid, we can convert it back to the other direction. Okay, so we've had acid chlorides and acid anhydrides and esters all reacting with alcohols. Now, amides don't react with alcohols under any of these conditions, and that's because the alkoxide produced is less basic than the amide that it would be displacing. Therefore, the alkoxide will never displace an amide to create it, so our amide is the most stable and will not react with any of the alcohols we have available to it. Okay, so let's take all those different acid derivatives and react them with ammonia or amines, okay? So if we take an acid halide and react it with ammonia or an amine, we can get a primary or a secondary or tertiary amide out of it, okay? Now we always have to use two equivalents of the amine because one of the equivalents is going to be consumed to make the amide, and the other equivalent is going to be making the HCl salt. Once you have you have to displace this chloride and it has to go somewhere. So it generates the HCl salt that has to be neutralized. So you always put two equivalents of either ammonia or a primary or secondary amine to form that amide and that salt, okay? So that works very quickly in this acid chloride reaction. What about when we use anhydrides, okay? So when we look at anhydrides, we again typically use two equivalents of ammonia or amine because the first equivalent will come in and displace an acetate ion and generate our amide here. Then we end up with a carboxylic acid. Remember, we dissolved carboxylic acids with ammonia or amines to make them more water soluble. So the first thing that's going to happen is that ammonia is going to act as a base, carboxylic acid is going to act like an acid. We have an acid-base reaction to generate this salt here. So just like before with the acid chlorides, we have to use two equivalency of the amine to generate first the amine and then neutralize the carboxylic acid derivative. Okay, now let's look at that reaction with esters, okay? So now we have ammonia reacting with an ester, and what we end up with is we only have to use one equivalent here. Because the species leaving is not acidic, we have the acetate ion or the chloride ion leaving, here we actually end up losing a neutral molecule of the alcohol. So in this case, we only have to use one equivalent of the nitrogen. It'll come in, displace this and kick it out and generate, and then we have to lose a proton to make it neutral again. And we'll generate a neutral equivalent of alcohol plus our new amides. Notice if you can use a primary, secondary, or ammonia to create a primary, secondary, or tertiary amide from the systems. Okay. So in general, once you form an amide, there's no driving force for it to react with other nitrogens to generate other amides. So once you form the amide, it tends to not react with other amines. So once you form the amide, it doesn't react with the alcohols or the amines. It's the most stable form. Okay, so that brings us to what this is our interconversion functional group table here. What this is telling us is that we can take any more reactive species and convert it into any of the other species. For example, the acid chloride can create an anhydride, an ester, an amide, or it can be hydrolyzed down with base to create to this acetate ion. The anhydride cannot be used to create that. It won't go in that direction, but it will be used to create the ester, the amide, or the acetate ion. The ester can't be used to create the anhydride. It can only be used to create the amide or the deprotonated species. The ester can be used to convert it to the amide, but the amide has to be hydrolyzed down with base to create that the carboxylic acid anion before it can do anything else. And then once you protonate it, we can then convert it back to the acid chloride. So the idea is the more reactive species can always make less reactive species. Once you get down to the amide, you'd have to hydrolyze it with base to get it back to the carboxylate ion before you can do anything else with it. And that concludes our first section of interconversions.